Hello. In this part of lecture, we are going to discuss the three examples which I have given in the first part of rigid pavement lecture. So the first problem was to determine the stresses due to thermal variation in the rigid pavement at the location given in this figure. So we have to determine the stresses at location 1, location 2 and location 3. Everything is known to me. That is the thickness of the slab, that means H, the modulus of subgrade reaction K. The increase in the temperature at the top of the pavement is 10 degrees Celsius and decrease in the temperature at the bottom of the pavement surface is 5 degrees Celsius. Also known to me is E value of the pavement, that 28 GPa, mu of the concrete, that is 0.15, and coefficient of thermal expansion of the concrete as 9 into 10 to power minus 6 per degree Celsius. You already know, due to the difference of the temperature from the top portion and the bottom portion of the rigid pavement slab, the pavement slab will wrap. Let's see how it's going to happen. So if you have changes in the temperature, you might resulting some tension, stresses in both the direction at center and on the edges in one direction. That stresses may be tension on compression depending upon whether you are measuring the stresses at the top and bottom of the pavement. So because of this stresses, your pavement is going to wrap either of this type or of this type. So this wrapping is happening due to the stresses you are calculating because of the differences in temperature. So let's calculate that stresses. We already know, in order to calculate the stresses due to variation in temperature, we will require these formulas. Uh, these formulas are helpful in order to calculate the wrapping stresses. So here in the interior part, your formula 1 will be required, and in order to calculate the stresses at the edges, formula 2 will be required. So if you see this formula correctly, what things you require? You require a E value which is given to you. You require a coefficient of thermal expansion which is already given to you. You require a T, that is difference in temperature, that will C, and you need to estimate the coefficient Cx and coefficient Cy. Mu is already given to you. So in this expression, all things except Cx, Cy and alpha is known to you. So let's estimate the value of Cx, Cy and D. So in order to calculate the value of Cx and Cy, we will require this graph. This graph is a plot between the values of Lx upon L and Ny upon L and Cx and Cy. In order to read this graph, we require two quantity, that is Lx upon N and Ly upon L. Let's come to your problem figure again. In the problem figure, what you know, that in x direction pavement length is 3.6 mm and in y direction the pavement length is 6 meter. Sorry, in x direction pavement length is 3.6 meters and in y direction pavement length is 6 meters. So the length is known to you. So Lx and Ly here is 3.6 and 6 meter respectively. The next step is to calculate the L, that means the radius of relative stiffness. The radius of relative stiffness can be calculated by using radius of relative stiffness formula, which is this expression. So here everything is already known to you. You know the elastic modulus E, you know the slab thickness, you know the modulus of subgrade reaction, you know the mu value. If you substitute these values correctly, you will able to estimate the L value of the slab. That comes out to be, E given to you is 28 GPa, that means 28,000 MPa. The slab thickness is given to you 0.2 in meters, 12 K given to you is 80, mu given to you is 0.15 to the power 2 whole power 1 by 4, and this will give you the value of L as 0.70 meters. Now L is known to you, Lx and Ly is also known to you, so you can calculate the Lx upon L and Ly upon L. So Lx upon L will be 3.6 divided by 0.7, and Ly comes out to be 6 upon 0.7. So values will be 5.14 and this value will be 8.57. Now Lx and Ly is known to you. Now concentrate on this chart corresponding to the Lx and Ly value. You we have to read the value of Cx and Cy. So as Lx by L value is 5.14, somewhat here that's um, sorry, it comes out to be in the middle 5.14, and here you need to read the value of Cx, and then the Ly upon L value is 8.57, so this will give you the value of Cy. So approximately let's quote this value. So let's take Cx and Cy as 5.14 corresponding value, that comes out to be 0.77, and Cy value corresponding to 8.57, that comes out to be 1.07. So we have to take the values of 0.77 and 1.07 as the value of Cx and Cy. Now in this formula, Cx and Cy estimated. Now the next thing which you have to estimate is this T, or difference in temperature between top and bottom of the slab. Now concentrate on this part, how we'll calculate the difference in temperature. So if I have given a slab, now the increase in the top of the slab is, let's suppose, is Ta, and decrease in the bottom of the slab is, let's suppose, Tb, and this is, let's suppose, the middle of your slab. So this temperature difference can be represented by two temperatures, one due to the uniform temperature and second by a equal temperature gradient, positive and negative, at the top and bottom. Now here, if you dissociate this Ta and Tb increments in two temperature, this uniform temperature will not result any wrapping, but it will give a pure bending. So this temperature is not responsible for wrapping. This is the temperature which is equally positive and negative at the top and bottom of the pavement, is responsible for your wrapping. So if you give this uniform temperature, so this uniform temperatures can be given by Ta plus Tb by 2. The second part of your temperature is given by Ta minus Tb by 2. This is also Ta minus Tb by 2, but this will be negative and this part will be positive. Now let's see how these two temperature will represent the Ta and Tb increment in the top and bottom of your pavement surface. So if you add TA plus TB by 2 plus TA minus TB by 2, that will give you TA, which was the increment at the top. Similarly, if you work out TA plus TB upon 2 plus, so this will be negative because this temperature is negative in nature. So TA minus TB upon 2, that will give you minus TB. Minus sign here represents that this temperature will be negative in nature or compressive in nature. This positive is that will give you a positive stress in the pavement. In our case, the increment at the top is 10 and decrease is 5. So let's calculate the gradient in our case. So if you calculate the uniform change, that will be TA plus TB by 2. So that will be 10 plus. Now here it is decrease in temperature, so we'll put minus 5 by 2. This comes out to be 2.5. This is the uniform temperature change which is not responsible for any wrapping. Let's calculate the temperature which is responsible for wrapping, that is TA minus TB by 2. So TA is 10 minus TB is minus 5 because the decrement by 2. So you will get a temperature of 7.5 degrees Celsius. So in this case, the difference in temperature T is 7.5 degrees Celsius. Now we can apply this formula to estimate the stresses at the center location. So let's apply this formula. Now everything is already known to me. So in order to calculate the sigma x, that means stress in x direction, that will be given by E times upon 2 Cx plus mu times Cy upon 1 minus mu square. Input the value. Value is known to you, that is 28 into 10 to the power 6. Multiplied by the Cx value, which you have estimated as 0.77, plus mu time, which is 0.15, multiplied by Cy, which you have estimated as, I think this step is clear to everybody. So once you have inputted this value, you will get a sigma x value as 1799.7 kPa. Similarly, you can estimate the value of sigma y. So in case of sigma y, you have to put Cy as Cx and Cx as Cy. So formula will remain same. 28 into 10 to the power 6 multiplied by 9 into 10 to the power minus 6 by 7.5 upon 1 minus 0.15. Sorry, here this square will be on 15 multiplied by, here the change will occur. This will become 1.07 plus mu times 0.77. This will give you the value of sigma y as 2292.2 K. So at center, you have stresses in x direction, hmm, that is 1799.7 kPa, and in y direction as 2292.2 kPa. Now these stresses are applicable on both top and bottom of the pavement slab, and in the top it will be tensile and in the bottom it will be compressive. Let's calculate the stresses on the edges. So to calculate the stresses on the edges, we'll require this formula. Here you can see in location 2 there is discontinuity in x direction, and in location 3 there is discontinuity in y direction. So if you are calculating in location 2, the stresses in n direction will be 0, and if you are calculating at location 3, the stresses in y direction will be 0. Let's calculate the other stresses. That means for location 2 and location 3, the value of sigma y. So the value of sigma y here will be given by Cy e sigma t by 2. Everything is known to you. Just input and you will get the desired value. Input the value. You will get the stress of 2068.5 kPa. Similarly, in case of sigma x, input the Cx e sin epsilon t by 2. Input the value, you will get a stress of 1488.8 kPa. So this is the solution of your problem number 1. Let's come to problem number 2. Compute the tensile stresses generated by subgrade friction in a 6-meter long concrete slab. So what happens if you have a concrete slab? The volume of the slab will be changes due to the variation in temperature or due to the seasonal variation. Also, the volume of subgrade may change due to the variation of temperature and reaction. So if this volume is changed, with respect to this, there will be a friction involved, and that friction will oppose this change in volume in this slab. So that's why there will be tensile stresses originated due to this friction. The frictional stresses due to seasonal changes in temperature can be calculated using this formula. Let's apply this formula in our case. So here L is 6 meter known to you, Y and F you already know. This is the value of gamma and this is the value of F. Put the value of gamma and F here in this expression. You will able to calculate the sigma due to friction. So sigma due to friction is L by 2, gamma coefficient of friction, the length is given to us as 6 to 0.5 into 1.5, and this, if you solve this, you will get 1 to 1.2, that will be in kPa. This is solution of question number. Let's come to question number 3. Determine the stresses in the corner, interior and edge point of 0.20 mm thick slabs under a uniform stress of 600 kPa distributed over circular area with a radius of 0.15 meter, given a modulus of subgrade reaction of 60 MPa per meter, an elastic modulus of 28 GPa, and a Poisson's ratio of concrete as 0.15. So here the first step is to estimate the load due to which the stresses will occur. So the load P here can be estimated by pi r square, whatever pressure is given. So pi radius is given to us, that is 0.15 square, into load is given to us, that is 600 kPa. Just solve this, you will get the load P, and this P will be used in the formulas further. Next step will be to estimate the value of L. So value of L you can estimate by using this formula. You know the every input here in this formula already given in the problem. Afterwards, you can simply apply these formulas to estimate the stresses at different location of the pavement. That will be the solution for example number 3. I think this resolves your all the doubt regarding the examples. So in the next lecture, we'll see about the design of rigid pavement using Austo procedure.